Imagine you spend months, like literally months, engineering this highly complex, computationally intensive data pipeline.
Oh, yeah, we have all been there. It is a massive undertaking.
Right. You map out every single transformation, you perfectly tune the aggregations, and it's just this absolute masterpiece of distributed logic.
And then the inevitable happens. Your organization decides to, migrate from an on-premise cluster to a different cloud provider entirely.
Exactly. Or maybe you just want to swap out your execution engine, get something significantly faster, hit the market, and suddenly you are forced to rewrite that entire code base from scratch.
Simply because the new environment relies on a completely different fundamental architecture.
Yeah.
Yeah.
Which is just a nightmare.
Oh, yeah.
So, welcome to the Deep Dive. I'm your host, and today we are tackling exactly that problem. Our mission is to demystify the world of big data processing by exploring a stack of sources that cover Apache Beam, Apache Spark, Google Cloud Dataflow, and maybe most importantly, the very real challenge of keeping your cloud compute costs under control.
Because that is a very real challenge. And I'm thrilled to be here. We are essentially going to shortcut the steep learning curve for you, synthesizing architectural comparisons and highly technical cost optimization strategies into, well, an accessible conversation.
Yeah, we want to give you those aha moments, whether you're prepping for a massive cloud migration, optimizing a pipeline, or just curious about how companies handle trillions of events. It all comes back to this holy grail of data engineering. What if you could write that complex pipeline logic just once?
Yes, exactly. Write once, run anywhere.
Right. Imagine writing a recipe just once, and suddenly it can be cooked perfectly in any kitchen in the world, no matter what ovens or pans they use. That philosophical battleground is what we're exploring today. But to understand why a framework like Apache Beam is revolutionary, we first have to look at the landscape it entered, right? A landscape overwhelmingly dominated by Apache Spark.
You really cannot talk about big data architecture without talking about Spark. I mean, it is the heavyweight champion.
It really is.
Yeah.
But I want to get under the hood here. What is the specific computational mechanism that allowed Spark to become such a dominant force?
Yeah.
Because before Spark, Hadoop MapReduce was the industry standard, right?
Yeah, and Hadoop MapReduce had a massive I/O bottleneck. Its architecture basically required writing intermediate data back to physical hard disks after every single stage of computation.
And disk I/O is incredibly slow.
Exactly. Just painfully slow for massive data sets. Spark changed the game by introducing RDDs, that stands for Resilient Distributed Datasets.
Okay, so how do those work?
Well, instead of writing to disk, Spark keeps the data entirely in memory. It takes a massive data set, partitions it across a cluster of machines, and processes those partitions in parallel using the volatile RAM of the worker nodes.
Okay, let's unpack the mechanics of that, because the distributed part makes logical sense. You're splitting a massive workload across multiple CPUs. But the resilient part is where the engineering gets really elegant.
It's brilliant, honestly.
Because if your entire data set is sitting in volatile memory, and a server in your cluster just suffers a hardware failure, you instantly lose that partition of data. How does Spark handle fault tolerance without just constantly copying data across the network? Because wouldn't that kill the performance gains?
Oh, replicating data in memory across a network is incredibly expensive, yeah. From both a compute and bandwidth standpoint, Spark actually bypasses that problem using lineage.
The lineage, like a family tree for data.
Kind of, yeah. An RDD doesn't just hold raw data. It acts as a deterministic log. It records the exact sequence of transformations, like the logical graph that was used to build that data set from the original source file.
Oh, I see. So if a worker node fails and an RDD partition just vanishes from memory, Spark doesn't panic.
Exactly. It doesn't panic at all. It simply looks at the lineage graph and recomputes only that missing partition from the underlying source data. It's an incredibly fast, self-healing mechanism. Plus, Spark has this massive ecosystem. I mean, huge community support, built-in machine learning, and SQL libraries.
So Spark is essentially a massive, highly optimized all-in-one factory. You write your production logic using their proprietary language, and they manufacture the output right there on their own integrated assembly line.
That's a great analogy. And this is the big, but there is a structural limitation to this factory model.
Right, especially when it comes to how Spark handles different velocities of data, like static batch data versus real-time streams.
Yes, that divergence is the critical limitation. In the Spark ecosystem, batch processing, which is, analyzing static bounded data like yesterday's closed transaction logs, and stream processing, analyzing infinite real-time data, they are treated as fundamentally different paradigms.
Meaning you basically have to write two separate pipelines.
Exactly. You essentially use one API like Spark Core or Spark SQL to author your batch jobs. But then when you want to stream data, you have to write against a separate module, historically something like Spark Structured Streaming, which processes streams by chopping them up into these tiny incremental micro batches.
And here is where the architecture takes a fascinating turn, because Apache Beam enters the picture and completely flips that tight integration on its head, right? Because Beam is fundamentally not an execution engine at all.
Right. It doesn't process a single byte of data itself, which is a wild concept when you first hear it.
It really is. It's purely a unified programming model.
Yes. You use Beam's SDKs to define the logical directed acyclic graph of your data pipeline. Basically, the exact transformations, the aggregations, and the windowing strategies you want to apply. But to actually execute that computation, you have to pass that graph down to a distributed processing backend.
Which Beam refers to as a runner. So if Spark is the all-in-one factory, Beam is, it's like being a master recipe developer. You write the recipe, the pipeline blueprint, but you can hand it off to be cooked in literally any kitchen.
Any kitchen you want. You can compile that blueprint to run on Apache Flink, Apache Samza, or, ironically enough, you can hand it right back to Apache Spark.
Wait, you can use Spark just as the runner for a Beam pipeline.
You absolutely can. You just use Spark as the execution runner. That separation of the logical plan from the physical execution is powerful. But for you, the listener, the true so what of Beam is the unified API.
Because developers do not write two separate code bases anymore.
Exactly. You avoid the technical debt of maintaining parallel pipelines. You author your transformation logic exactly once, and the Beam model applies that identical code to both bounded historical batch data and unbounded live streaming data seamlessly.
Okay, but claiming you can seamlessly process a fixed batch of data and an infinite stream of data with the exact same code base. I mean, that sounds incredible on paper, but how does the engine actually pull that off dynamically without crashing?
It's a fair question.
Because if I ask a compute cluster to run an aggregation on an infinite stream of data, it's just going to count forever, right? It'll never return an answer.
Right, it would just hang indefinitely. So Beam manages infinity through a core abstraction called a P collection.
A B collection.
Yeah. You can think of a P collection as the fundamental data structure in Beam. It represents an unordered data set. And a P collection can be bounded, meaning it has a fixed known size, like reading a complete database table. Or it can be unbounded, representing an infinite stream of continuous events.
So to perform aggregations on an unbounded P collection, Beam has to rely heavily on windowing. You basically have to slice infinity into mathematically manageable pieces.
Exactly. Slicing infinity. Windowing logically subdivides the unbounded data stream based on the event timestamps attached to each record. So instead of trying to aggregate every click that has ever happened in the history of a website, you instruct the pipeline to aggregate all the clicks that occurred, say, specifically between 1.00 p.m. and 1.05 p.m.
And Beam supports a few different types of windows, right?
Yeah, it supports fixed windows of specific durations, sliding windows that overlap, which is great for rolling averages, and even complex procession windows.
Oh, procession windows. That's where it groups data dynamically based on bursts of activity from individual users, right?
Got it.
Okay, let's put this into a concrete, real-world scenario to test the limits of this architecture. Let's say you're processing telemetry data for a global mobile app. A user finishes a task, and their phone transmits an event to your server.
Okay, so that's our unbounded stream.
Right, and we're slicing it into 5-minute fixed windows. But mobile networks are notoriously unreliable. Say a user loses cellular signal at 1:04 p.m. They don't reconnect to a tower until 1:15 p.m., at which point the phone finally uploads the event.
Ah, the classic leak data problem.
Exactly. And this brings us to the mechanism of the watermark. The sources explain that the system uses the watermark to determine when a window should be closed. But fundamentally, a watermark is a heuristic. It's an internal, algorithmic guess by the system that all the data for a specific window has arrived.
Right. It tracks the progression of event time relative to the pipeline's processing time.
But I have to push back hard on this reliance on a guess. I mean, we are talking about enterprise-scale architecture here.
It does sound risky when you put it like that.
Right. The sources mention Booking.com pushing over 2 petabytes of data a day through Beam. HSBC relies on it to manage global credit risk models. How can an architecture operating at that scale possibly rely on a heuristic guess?
That's a very valid concern.
Because if the watermark declares the 1.00 to 1.05 window closed at 1.07, and that late mobile event, or worse, a delayed financial transaction arrives at 1.15, discarding that data is a massive operational liability. You cannot just drop valid enterprise data because a network switch lagged.
No, absolutely not. Dropping critical enterprise data is unacceptable, but the watermark is necessary as the system's internal clock. It has to make a call eventually. However, it does not strictly dictate data destruction.
Okay, so how does it save the late data?
To handle the exact scenario of delayed networks, Beam provides developers with a mechanism called triggers. Triggers define when the results of a window are physically emitted to the downstream sink, and they allow you to safely override the default behavior of the watermark.
Oh, wow, so it decouples the windowing logic from the output logic entirely.
Yes, it gives you granular programmatic control. You can configure a trigger to emit early speculative results. So you might tell the pipeline, hey, update the downstream dashboard every single minute, even though the 5-minute window hasn't closed yet.
So the business gets a real-time approximation.
Exactly. And then you configure a late firing trigger. You instruct the system, after the watermark passes, retain this window's state in memory for an additional hour. If any late arriving data shows up, recompute the aggregation and emit an updated result.
That is brilliant. You are actively managing the fundamental trade-off between low latency, getting a fast answer, and absolute correctness, getting the perfect answer.
And the developer gets to dictate exactly how those late corrections behave. You can configure them to operate in accumulating mode, where the trigger emits the entirety of the newly updated aggregation.
Or a discarding mode, right? Where it only emits the isolated delta of the late arriving data.
Exactly. It depends entirely on what your downstream database is engineered to ingest. And the scale this unlocks is just staggering. I mean, LinkedIn utilizes this architecture for over 3,000 parallel pipelines, processing 4 trillion events daily.
4 trillion events
Oh,
daily. That proves the resilience of the blueprint. But, as we established earlier, Beam is just the logical blueprint. It still requires a physical execution engine to actually run.
it does. It needs a kitchen.
Right. And for organizations leveraging Beam, according to the sources, the ultimate execution engine for this is Google Cloud Dataflow.
Yeah, Dataflow is deeply tied to Beam. Beam actually originated from Google's internal data processing systems. They open-sourced the SDK to the Apache Foundation, but Dataflow remains Google's fully managed proprietary execution engine, engineered specifically for this model.
And the core value proposition of Dataflow is its serverless architecture, right?
Yes, serverless is the key word here.
But when we say serverless in the context of big data, we aren't talking about simple cloud functions. We are talking about completely abstracting away the massive operational overhead of cluster provisioning.
Which is usually a nightmare for data engineers. In traditional infrastructure models, engineers are constantly provisioning worker VMs, monitoring memory utilization, and basically just hoping they didn't under-provision right before a massive spike in traffic.
Because if they do, the pipeline inevitably crashes. Or conversely, they over-provision out of fear and end up paying exorbitant hourly rates for compute instances that just sit idle 90% of the time.
Exactly. Dataflow solves this by dynamically autoscaling the underlying infrastructure. It continuously monitors the back pressure of the incoming data queue, and it automatically spins up new worker nodes to parallelize the processing workload. And then, crucially, it gracefully spins those nodes back down when the queue clears.
It's the architectural difference between hiring a team of manual laborers to constantly dig and redirect trenches for water versus installing a smart plumbing system that just automatically widens the pipes whenever a flood is coming.
That is the perfect analogy. You don't have to manually reroute traffic or rack new hardware. The compute layer simply expands to absorb the state, processes the transformations, and contracts back to baseline.
Which is particularly effective for hybrid cloud deployments. Large enterprises need to seamlessly connect massive legacy on-premise databases like SAP or Oracle into modern cloud analytics warehouses without ripping out their existing infrastructure all at once.
It allows organizations to transition away from maintaining rigid, brittle integration pipelines. For the listener, this is the big takeaway. You can shift your engineering focus from managing compute infrastructure to actually generating real-time intelligence using a flexible, consumption-based model.
And that brings us to the most painful reality of modern cloud architecture, the phrase consumption-based model.
Oh, the billing.
Yeah. It sounds brilliant in a system design meeting because it implies infinite scalability. But it is terrifying to a finance department because an infinitely scaling pipeline generates an infinitely scaling cloud bill.
It really does, if you aren't careful.
Right. An architecture that automatically spins up 1,000 vCPUs to handle a data flood is going to charge you for every single second of that compute time. So we need to talk about taming the beast. How do you keep data flow costs strictly under control?
Well, cost optimization has to be treated as a first-class engineering metric, right alongside latency and throughput. With data flow, you have to conceptually separate your direct compute costs from your indirect architectural costs.
Okay, let's break that down. Direct costs are the resources Google bills you for directly to execute the pipeline, right? Like the vCPUs, the memory footprint, the persistent disks attached to the worker nodes.
And the usage of managed back-end services, like Dataflow Shuffle.
Let's pause on the shuffle service for a second, because that represents a major architectural shift. In a distributed join or a massive aggregation, you have to move petabytes of intermediate data between the individual worker nodes to group things correctly.
Yeah, that shuffle operation is incredibly resource-intensive.
If the worker VMs handle the shuffle themselves, you have to provision massive, expensive VMs with huge local solid-state drives just to handle the I/O.
But offloading that specific operation to Dataflow's dedicated back-end shuffle service fundamentally changes the compute profile. It allows you to provision significantly smaller, cheaper worker VMs because they no longer have to manage that intermediate state on their local disks.
Which is a huge win. But managing those direct compute costs is only half the battle.
Yeah.
The indirect costs are where organizations really hemorrhage money, right?
Oh, absolutely. A Dataflow pipeline doesn't operate in a vacuum.
Right. If your pipeline is aggressively polling pub/sub for messages or executing highly parallelized continuous writes into BigQuery, you are racking up massive API and storage costs on those external services.
And this leads to a huge misconception.
Yeah, because logically, one might assume that if I optimize my pipeline code to execute 50% faster, I should be cutting my cloud bill in half because I am renting those vCPUs for significantly less time. Speeding up the pipeline should inherently save money.
Right, but that assumes a linear correlation that simply does not always exist in distributed systems. Faster pipelines are usually cheaper, but not always.
Wait, really? How does making it faster cost more?
Because making a pipeline faster often requires dramatically increasing parallelism, which triggers aggressive autoscaling. You might process a massive historical load in 1 hour using 100 VMs, or you could process it in 10 minutes using 1,000 VMs. The direct data flow compute cost might be roughly identical for both scenarios.
Oh, I see. But hitting BigQuery with 1,000 concurrent highly parallelized connections might drastically increase your API utilization costs.
Exactly. Or it could trigger expensive quota limits. You simply shift the cost from direct data flow billing to indirect API billing. You have to map the total cost of ownership across the entire ecosystem.
Speed does not equal savings if it just shifts the bottleneck to a more expensive API. That is a crucial takeaway. So we need to look at the actionable, highly technical levers available to actually pull these costs down. For heavy batch workloads, the mechanism that immediately stands out in the sources is FlexRS.
Flexible resource scheduling. It is a massive lever for cost reduction. If you have a batch job that is highly latency tolerant, meaning it does not need to complete instantly, such as a nightly reconciliation job or a weekly historical data load, you enable the FlexRS flag.
And what does that do?
Dataflow will pool standard VMs with heavily discounted spot or preemptible instances, and it will intentionally delay the job's execution within a 6-hour window to find the absolute cheapest available compute capacity across the region.
Leveraging a 40% compute discount simply by telling the system to run a job whenever the hardware is cheapest. That is a massive optimization. But what about streaming jobs where you cannot delay execution? I want to unpack the worker limits, specifically the tension between the num workers and max number of workers parameters.
Right. Those parameters define the absolute boundaries of your autoscaling behavior. Num workers sets your cluster's baseline.
So if you know you are processing a massive, predictable backlog of data, you do not want the system to start with one worker and spend 20 minutes slowly calculating that it needs to scale up.
Exactly, because every time the cluster scales, it has to pause and physically redistribute the data state across the newly provisioned workers. By setting a high initial numWorkers parameter, you completely bypass that operational overhead.
And max number of workers acts as your financial circuit breaker, right?
Yes, if a downstream API experiences latency, causing back pressure in your pipeline, Dataflow's default reaction is to aggressively throw more compute resources at the problem.
Which means if you fail to cap the maximum workers, you could easily wake up to a cluster of 1,000 VMs fighting a downstream bottleneck they cannot actually fix.
Which is a very expensive way to wake up. Interestingly, in certain architectural patterns, the autoscaling feature itself becomes a financial liability.
Wait, you mean you should actually disable auto-scaling sometimes?
Yeah. For short-lived batch jobs or pipelines with highly predictable, constant throughput, the constant telemetry polling and computation required for the system to evaluate whether it should scale adds unnecessary overhead.
Oh, so statically provisioning the exact cluster size you need is often significantly cheaper than paying for the auto-scaling intelligence.
Exactly. And if we want to get even more granular, we have to talk about tuning the actual Java virtual machine running on the underlying worker nodes.
Yes, the JVM tuning. Because in data-intensive pipeline transforms, memory management dictates performance. If the JVM has to constantly pause your pipeline execution to clean up heap memory, you are paying for dead compute time.
Garbage collection pauses are the silent killer of streaming performance. For exceptionally heavy workloads, the default garbage collector will just struggle to keep up. But developers can pass a specific pipeline option. Experiment Javag uses ZGC.
And that instructs the underlying workers to utilize the Z garbage collector, which is engineered specifically for massive memory heaps and sub-millisecond pause times.
Right. By optimizing how memories are reclaimed, you prevent out-of-memory worker crashes. And you can actually run your entire pipeline on a much smaller, cheaper instance class.
But I mean, dropping an experimental garbage collection flag into a production environment just to shrink the heap size sounds terrifying.
Oh, it is. You shouldn't just do that blindly.
Which underscores the absolute necessity of test harnesses. You cannot just push ZGC tuning or aggressive worker caps directly into production and hope your pipeline survives the weekend traffic spike. Both of us agree strongly on this.
Integration testing at scale is non-negotiable. You have to simulate production loads. By utilizing tools like Google's streaming data generator templates, engineering teams can accurately model the back pressure, monitor how the autoscaling responds, and confidently forecast the billing impact of these configurations before they ever touch the production environment.
Let's pull all of these architectural threads together for the listener. We have explored a massive paradigm shift in how we build distributed systems. We looked at how Spark revolutionized in-memory parallel processing with RDDs, and how Beam abstracted that logic entirely.
Allowing developers to author unified batch and streaming pipelines capable of executing on literally any runner.
Right. We broke down the underlying mechanics of handling infinite data streams using complex windowing to slice the data, and relying on watermarks and triggers to tame the inherent chaos of late-arriving events across unpredictable networks.
And we saw how deploying that logical blueprint onto a serverless runner like Dataflow eliminates the operational nightmare of manual infrastructure management, replacing static hardware provisioning with dynamic, self-healing scaling.
And most importantly, we unpack the deep technical levers from FlexRS scheduling to JVM memory tuning required to keep the financial cost of that dynamic scaling strictly under control.
It really represents a comprehensive evolution in how organizations extract intelligence from raw data at a global scale.
It does. And it leaves me with one final kind of provocative thought for you to consider. We spent this entire deep dive discussing Apache Beam's core philosophy, isolating the logical recipe from the physical kitchen.
The Holy Grail.
Exactly. And right now, our compute kitchens are built on classic CPUs and increasingly GPUs. But the hardware landscape is on the verge of a seismic generational shift. We are rapidly approaching the era of quantum computing.
Which will change everything.
Exactly. As our execution environments make that massive leap from classical binary processing to quantum states, the underlying hardware architectures will become entirely unrecognizable. So the question is, as hardware evolves exponentially faster than software, could writing your code base in highly abstracted runner-agnostic frameworks like Beam be the only way to ensure your data pipelines survive?
Will this unified logical blueprint be the architectural bridge that allows today's data logic to seamlessly execute on tomorrow's quantum compute engines?
It's definitely something to think about as you design your next pipeline. Thank you for joining us on this deep dive. Keep exploring, stay curious, and we'll see you next time.